All right, today we're looking at our day 2 of polar areas. Today is focusing more on some of the other ways they can ask polar area questions. This starts with finding the intersection of two polar curves. So we have two curves here. We have the first one, which is r equals 1. That's a circle around 1, or second one. And the second one is r equals 1 minus cosine theta. So that's going to be here, 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 here. It's a cardioid that looks like this. And we're looking for the intersection. It's pretty obvious looking at here where the intersection might be, but we should still calculate it just to make sure. 1 equals 1 minus cosine theta. Subtract the 1. Cosine's equal to 0 at pi over 2 and 3 pi over 2. There we go. So those are our points of intersection. Now, the reason this is important is because they'll ask questions like this. Find the area inside of r equals 2 and outside r equals 2 minus 2 cosine theta. So they just made this one a little bit bigger. There's r equals 2. There's 2 minus 2 cosine theta. Okay? And so inside of r equals 2, but outside 2 minus 2 cosine theta is this part right here. All right, so a lot of y'all are saying, okay, so we have some intersections that we just had to find. Those are going to be our bounds, but it's going to be a little bit tougher than that. So when we look at this, we need to consider the outside and the inside. Remember, everything is coming out from the origin here. So the outside function will be the blue one, or equation will be the blue one. So we have r equals 2 is the outside, and then r equals 2 minus 2 cosine theta is the inside. So if we're going to find the area in between them, we're going to do outside minus inside. So 1/2 integral 2 squared d theta minus 1/2 integral 2 minus 2 cosine theta squared d theta. The issue is the bounds we just found are not going to work. If we do pi over 2 to 3 pi over 2, that's going to take us around this way. And that's not the side of the graph we need. We need to have the same two intersections, but go around the other way. And a lot of people will say, well, can't we just go 3 pi over 2 to pi over 2? Well, that just goes the same side, but goes this way. So it's still the same side, just going the opposite direction. So we need a different angle for down here. So we would use negative pi over 2 instead. And so we have negative pi over 2 to pi over 2, negative pi over 2 to pi over 2. And then we'll combine them because they have the same coefficient and same bound. So we have 1/2 integral from negative pi over 2 to pi over 2 of 4 minus and then 2 minus 2 cosine theta squared d theta. All right, this would probably be a calculator question or it's set up but do not solve question, but it's still nice to be able to see. Another one is one like this, and we're going to make a change here. We're going to change this from 2 plus 3 sine theta to 2 plus 4 sine theta, so that the numbers work out a little bit better. This is an inner loop problem. Oops, wrong spot. 6 is going to be somewhere up there, 2 is there, and so we have this right here. Leave this on with an inner loop, nothing too crazy. But it wants the area outside of the inner loop. It wants this area right here. Well, a lot of people are saying, oh, well, similar to how we found the inner loop yesterday, we'll just do that same thing. But there's an issue. Okay? If we go and we start shading what we're graphing, because remember, we go all the way from the origin out to the side, if we shade it, we're going to end up shading the inner loop once there as we go around the outside. And then we're going to shade it again as we go around the inside of the inner loop. So the graph kind of shades the inner loop twice when you go from 0 to 2 pi. So we need to start by figuring out what these are. These inside and outside parts. So similar to how we did last video. 2 plus 4 sine theta. Sine theta equals negative 1/2. And that's going to be 5/6, yeah. So 7 pi/6 and 11 pi/6. But 7 pi/6 and 11 pi/6 are the start and end of the inner loop. That goes in here. We need the outer loop. We will use that. This is the inner loop. So 7 pi/6 to 11 pi/6, 1/2, 2 plus 4 sine theta d theta, square d theta. That's going to be useful, but we're going to need to subtract that out as we go around the outside. So if this is 7 pi/6, this is 11 pi/6, then we need to go from 11 pi/6 all the way around back to this other side. We have a few ways we can do that. We can just add 2 pi to 7 pi/6 and make this 19 pi/6. That works. Or if we would rather keep 7 pi/6 and work with better numbers, we can say this is going to be negative pi/6 all the way around to 7 pi/6. Now, as we go around there, as we go around this outside, it's going to get shaded and that inner loop is going to get shaded. So what we want is we want this area on the outside, the 1/2 integral from negative pi/6 to 7 pi/6, 2 plus 4 sine theta squared d theta. We want that, and we want to subtract the inner loop because it's shading in the inner loop as we go all the way out to here. And we don't want the inner loop at all. So we're going to subtract out the inner loop that we found there. Now, this one, unlike the last one, can't be combined because the bounds are not the same. So we would have to do them as two separate integrals. Once again, a setup or calculator problem. All right, next we're going to talk about length of the polar curve. Length of the polar curve is just this formula. And let's change this. Let's use r. So r of theta and r prime of theta. Integral from a to b. So for a problem like this, we have a cardioid. 2 minus 2 cosine theta. We're going to find the length around that cardioid. So we'll do the integral from 0 to 2 pi because that's the length, or that's the distance around the cardioid. Square root of r, which is 2 minus 2 cosine theta squared, plus the derivative of r prime. That's going to be just 2 sine theta. And then we, in this case, plug it in the calculator. You can solve this one by hand. We figured out how to do it in class. So if you want to ask, feel free to stop by and ask, and I can show you. It involves the half angle identities. But aside from that, you plug in the calculator, you solve. That would be the area, or the length around the curve. It would be how long around this curve is. Now, the key with these, similar to with area, is you have to make sure you understand your bounds. You want to make sure your bounds cover the parts of the curve you want. So if it's a rose curve and it just wants the length around one petal, you need to make sure the bounds cover the length of one petal. All right, that's it for me. Y'all let me know if you have any questions. You have a great day.